Hey guys, good evening. Good evening again, and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So, my dear students, if I'm perfectly audible, visible to every one of you, just quickly let me know in the chats. Just quickly let me know in the chats if all of you can hear me. If I'm perfectly audible, visible to every one of you, quickly let me know in the chats, people. Everyone. Everyone means everyone. Yeah. Let me know quickly in the chats if I'm perfectly audible, visible to every one of you. Quickly, my dear students. Good evening, people. Good evening. Good evening and welcome back. Good evening and welcome back. Good evening and welcome back. So, as you all must be knowing, today we are going to do one of the highest weighted chapters of chemistry, right? Particularly from inorganic chemistry, from which every year almost like 3 to 4 questions are asked in your NEET examination. Okay? And I shall be completing this particular chapter in 2 parts. Part number 1 is today, and part number 2, that is going to happen tomorrow. Yeah? Right? Perfect. So, all ready for the session, my dear students? All ready for the session? All ready for the session? Perfect, guys. Perfect. So today we shall be doing what? We shall be doing chemical bonding, right? Today we shall be doing chemical bonding. Yeah. Okay. So should we start, people? Guys, don't worry. All the chapters will be done. Just today is the time for chemical bonding. Let's cover this particular chapter first. Well, all those students who are thinking that they have not studied this particular chapter before, whether they will be able to understand this particular chapter if they watch it right now, the answer is a big yes. You need not to worry. Because every topic which I shall be discussing with all of you, I'll be doing every topic from the basics, from the scratch, as if you have never studied this particular chapter before. Okay? So you need not to worry about that. Everything will be started from the scratch only, from the basics only. Okay? Perfect, guys. So without wasting a lot of your time, let's get going. Let's get started. Yeah? Let's get going. Let's get started. So first of all, how do we exactly define the term chemical bond? What is a chemical bond? Let's talk about that first. What is a chemical bond? Duration of the session will be 3 hours. Okay, don't worry. 3 hours. How do we define the term chemical bond? My dear students, it's pretty much simple. Any force of attraction that holds the constituents together in a molecule. Let me write the definition for you. I'll write any force of attraction that holds the constituent particles which can be ions, which can be atoms, right? That holds the constituent particles together in a chemical species. Is what we call as a chemical bond. So what does that mean? My dear students, as I've written exactly the definition of it, any force of attraction that holds the constituent particles together in a chemical species. That force of attraction is what we call as the chemical bond. For example, For example, you have got NaCl molecule. You have got NaCl molecule. You know, in case of NaCl, you have got basically Na positive and Cl negative. And in case of Na positive and Cl negative, there will be force of attraction. And any force of attraction that holds the constituent particles together in a molecule, you call this force of attraction as a chemical bond. You call this force of attraction as a chemical bond. For example, talk about H2 molecule. Talk about H2 molecule. When you talk about H2 molecule, you will find between two hydrogen atoms, there will be some force of attraction which will be holding these atoms together. And that force of attraction is again called as a chemical bond. So what is a chemical bond in short? Chemical bond is nothing but it is the force of attraction that holds the constituent particles, which can be atoms, which can be ions, together in a chemical species, right? Now, my dear students, we have got different types of chemical bonds, out of which the first chemical bond which we are going to discuss, what is that? That's going to be your ionic bond. Well, I'm going to keep the content very crisp. Whatever things can be asked in your examination, right? I'll be talking about those things to be very precise, okay? I'm not going to go into the very much depth. Whatever things are required for your NEET examination, I'll be only talking about those things here, okay? I'll be only talking about those things here. So, my dear students, the first type of the chemical bond is what you call as ionic or covalent bond, ionic or electrovalent bond. What is an ionic bond, first of all? First of all, in order to make you understand the ionic bond, let me take the case of NaCl molecule. Let me take the case of NaCl molecule. If you talk about NaCl, how many elements do you see here? We'll say two elements. One is sodium, one is chlorine. One is sodium and one is chlorine. And you must be knowing, sodium is basically a metal. Chlorine is basically a non-metal. Sodium is a metal and chlorine is a non-metal. And you know, metals have got the tendency to lose electrons and non-metals have got the tendency to gain electrons. Metals have the tendency to lose electrons, and when it comes to non-metals, non-metals have got the tendency to gain electrons. Now, if you particularly talk about sodium, sodium's configuration is 2, 8, 1, right? And chlorine's configuration is 2, 8, 7. You know that already? Okay. Now, my dear students, tell me one thing. How many electrons are there in the outermost shell of sodium? 1 electron. So, is it possible for sodium to gain 7 electrons? Or I would say it is easier for sodium to lose 1 electron. I would say it is easier for sodium to lose 1 electron, due to which it gets converted into Na positive. So I would say the sodium, it has lost 1 electron completely, got converted to Na positive. Now chlorine, since it has got 7 electrons in its outermost shell, so is it easy for chlorine to lose all the 7 electron, or it is easier for chlorine to gain 1 electron? I would say it is easier for chlorine to what? It is easier for chlorine to gain 1 electron. And when chlorine gains 1 electron, it gets converted into Cl negative, right? So I would say sodium has lost 1 electron completely and chlorine has gained that 1 electron completely. Due to which, what happened? Cation formation took place as well as the anion formation took place. Cation formation took place as well as the anion formation took place. Now, my dear students, between two equal and oppositely charged species, can I say between them there will be electrostatic force of attraction? There will be electrostatic force of attraction because this is positive, this is negative. There will be attraction. And this electrostatic force of attraction, which holds these ions together, this electrostatic force of attraction that holds these ions together, what do we call that as? We call this particular bond here as the ionic bond. We call this particular bond here as the ionic bond, right? Or you can call it as the electrovalent bond as well. You can call it as electrovalent bond as well. Okay, you call it as the electrovalent bond as well. So if you want me to define the ionic bond or electrovalent bond, I would say ionic bond or electrovalent bond, it is basically the electrostatic force of attraction between the cation and anion, which is formed by the complete loss and the complete gain of electrons. Which is formed by complete loss and gain of electrons. As you saw, sodium has lost its one electron completely. Chlorine has gained that one electron completely. So there is complete loss and gain of electrons happening. And due to the complete loss and gain of electrons, which bond gets formed? It is going to be the ionic bond. And my dear students, that particular compound which contains the ionic bond, that particular compound you directly call as ionic compound. That particular compound you directly call as ionic compound. Perfect. I believe all the things still here are clear to everyone. If yes, let me know once in the chats quick. Yeah. I'm going to tell you a lot of tricks as well. Just wait. Did you understand what a chemical bond exactly is all about? All right. Now, my dear students, the point is, what are the favorable conditions? What are the favorable conditions for the chemical bond? Favorable conditions for, ionic bond. Favorable conditions for ionic bond. So first of all, let me tell you, for the formation of ionic bond, I would say one element should be metallic and another one should be non-metallic. So basically, one element should be metallic, another one should be non-metallic. Why is that? Because when one element will be metallic, it will be losing the electron. When the other element will be non-metallic, it will be gaining the electron, due to which cation and anion formation will take place. So I would say first of all, for the formation of ionic bond, one element definitely must be metallic, another one should be non-metallic, so that the metallic one will lose electron and non-metallic one will gain electron, due to which cation formation and anion formation will happen. And once cation and anion formation takes place, there will be electrostatic force of attraction between them. As simple as that, right? My dear students, point number two. I would say metals should have low ionization energy. Metal should have low ionization energy. Why is that? Because if the metal has low ionization energy, it will be easier for the metal to form the cation. If the metal has low ionization energy, it will be easier for the metal to form the cation, right? And that particular metal which can form cation easily, that metal is the perfect candidate for the formation of ionic bond. As simple as that. Similarly, if you talk about non-metal, I would say non-metal must have, or I should write should have, high electron gain enthalpy. High electron gain enthalpy. Why is that? Because when the non-metal will have high electron gain enthalpy, then that non-metal can form the anion easily, right? That non-metal can form the anion easily. And once the non-metal forms the anion easily, I would say that particular non-metal which can form anion easily, that is going to be the perfect candidate for the formation of ionic bond, right? Is that clear to everyone? So what are the favorable conditions, my dear students? What are the favorable conditions? I would say in simple words. If I talk about the ionic bond, in case of ionic bond, the metal, one element should be metallic, another one should be non-metallic, right? Point number one. Point number two, metals should have low ionization energy. Non-metals should have high electron gain enthalpy, due to which formation of cation and anion will be easy, right? And due to which, and this ionic bond formation will be easy as well. Okay? I believe this is clear to everyone. Okay? Now, my dear students, about these ionic compounds, they have got certain characteristic features. There are certain characteristic features about these ionic compounds. What are those? My dear students, first of all, in case of ionic compounds, there is electrostatic force of attraction between the ions. And you know, electrostatic force of attraction is a very strong force, right? If it is a very strong force, if it's a very strong force, what's going to happen? What's going to happen? The ions are going to be very close. Perfect. So I would say, since due to the presence of very strong electrostatic force of attraction, these ionic compounds, they are generally hard. Number one, because of the presence of very strong electrostatic force of attraction. Point number one. Point number two, due to the presence of very strong electrostatic force of attraction, they have got very high melting and boiling points. Due to the presence of very strong electrostatic force of attraction, I would say they have got very strong melting and boiling points as well. And my dear students, in solid state, they behave like insulators. Whereas in molten state and aqueous state, they are going to behave like the conductors. Right? This is one more important point which you need to remember. Perfect. And similarly, since there is very strong electrostatic force of attraction, due to which these ionic compounds, they will be having high density as well. These are some important characteristic features which you should remember about these ionic compounds. Point number one, they are generally hard because of the presence of strong electrostatic force of attraction. They have got high melting and boiling points. Why is that? Again, because of strong electrostatic force of attraction, right? And in solid state, they behave like the insulators. In molten and aqueous state, they behave like the conductors, right? And at the same time, because of the presence of high electrostatic force of attraction, they have got high density as well. Perfect. Some important points which I would want you guys to remember directly. No need to go into the very much details of it. Okay. Now, people, when it comes to the ionic compounds, there are some terminologies which are related to ionic compounds. Okay. The first terminology which we are going to discuss about the ionic compounds, what is that? That is your lattice energy. Which we represent with delta H lattice. Now, how do we define this lattice energy? This is one of the definition which is written here. But let me give you one more definition which will make things more clear to you. What is that? I would say the amount of energy. The amount of energy required. The amount of energy required to break. The amount of energy required to break 1 mole of an ionic lattice. The amount of energy required to break 1 mole of an ionic lattice into its constituent gaseous ions. What does that mean? Let's try to understand. Pretty much simple, guys. Just have proper eye on the screen. For example, let's say I've got 1 mole of ionic lattice. I've got 1 mole of NaCl solid. Let's say I've got 1 mole of NaCl solid. Now, in NaCl solid, I would say this is your Na positive, this is your Cl negative. And there will be force of attraction between Na positive and Cl negative. That force of attraction is basically your electrostatic force of attraction, right? Now, to break this ionic compound into its constituent gaseous ions, what do we need to do? To break this ionic compound into these constituents, can I say I need to break this force of attraction? This force of attraction should be broken down. And to break the force of attraction, energy is required. My dear students, the amount of energy that is required to break 1 mole of an ionic lattice into its constituent gaseous ions, that energy required is what you call as the lattice energy, right? Perfect. So over here, we are breaking 1 mole of NaCl solid into its constituent gaseous ions. And for this particular purpose, whatever energy is required, that energy required is what you call as the lattice energy, in short. Perfect. Or you can say one more thing. You can say, if you look at this particular definition, it is the amount of energy released. When 1 mole of an ionic lattice is formed. So if you do the reverse of it, I'll say something like this. Since 1 mole of an ionic lattice is getting formed, from its constituent gaseous signs. Since Na positive, Cl negative, they'll attract. Whenever there are attractions, energy is released. Whenever there are attractions, energy is released. The amount of energy that is released when 1 mole of an ionic compound is formed from its constituent gaseous signs, that's also called as lattice energy. The choice is yours with whatever way you want to define it, right? But you can, to have a feel of it, you can remember it like this. The amount of energy which is required to break 1 mole of an ionic lattice into its constituent gaseous signs. Okay? At the same time, guys, lattice energy, it gives the idea about the stability of ionic compound. Lattice energy, it gives the idea about the stability of ionic compound. Remember, that particular ionic compound which has got more lattice energy, what does that mean? The ionic compound which has got more lattice energy, that means more energy is required to break the ionic compound its constituent gaseous signs. If more energy is required to break the ionic compound its constituent gaseous signs, that means the ionic compound, it does not want to break into the constituent gaseous signs, which technically means this ionic compound is basically stable, right? Perfect. So remember, stability of an ionic compound is directly proportional to what? It is directly proportional to lattice energy. Higher the lattice energy, more stable will be the ionic compound. As simple as that. Okay. Now this lattice energy, it basically depends on two parameters. If I talk about this lattice energy, it depends on two parameters. On what parameters? It is directly proportional to the charge on the ions and inversely proportional to the size of the ions. Directly you are going to remember. Directly you'll be remembering all this stuff. Okay? Yeah? Lattice energy, it's directly proportional to the charge on the ions, inversely proportional to the size of the ions. Well, you can relate this directly with what? You can relate this directly with your Coulomb's law, right? F is equal to K Q1 Q2 divided by R square. More the charge, more is the force of attraction. More the force of attraction between the ions, more energy is required to break it. Simple. Or you can say it like this as well. Lesser the size of the ions, closer the ions will be. Closer the ions, that means lesser the distance between the ions. Lesser the distance between the ions, more will be the force of attraction between them. More the force of attraction between the ions, more energy is required to break it. That means more is the lattice energy. Simple. So directly remember, your lattice energy is directly proportional to charge, inversely proportional to size. Okay. Now, my dear students, can you tell me the order of lattice energy here? LiCl, NaCl, KCl, RbCl. First of all, this is basically Li positive, Cl negative, this Na positive, Cl negative, K positive, Cl negative, Rb positive, Cl negative. Let me tell you, this anion everywhere is same. So I'm not going to decide on the basis of anion. I will have to decide as per cation. Right? Now, the charge on every cation is same. So you are not going to decide on the basis of charge. You will be deciding on the basis of size. And we know, lesser the size, more the force of attraction, and more is the lattice energy. Right? So Li positive, Na positive, K positive, Rb positive. You already must be knowing Li positive, Na positive, K positive, Rb positive. What happens when you move from top to bottom? The ionic size increases. So Li positive will have least size. Lesser the size, more the attraction between the ions, and more the lattice energy. So this is the order of lattice energy in short. Right? This is the order of lattice energy in short. You are going to decide as per charge first. First priority will be given to the charge. Second priority will be given to the size. Right, people? Now look at this one. This is Mg di positive. This is O di negative. Na positive, Cl negative. Li positive, Cl negative. More the charge, more the lattice energy. So this will have maximum lattice energy, Mgu, because charge is more on the ions. Now, Cl negative, same. Charge on cations, same. Talk in terms of size. Lesser the size, more the force of attraction. More energy is required to break it. So this will be on second number. This will be on third number. Right? So this is going to have maximum lattice energy, followed by LiCl, followed by NaCl. As simple as that. Okay. Now, my dear students, there comes one more term. What is that? That's called as hydration energy. What is hydration? First of all? For example, imagine that this is a container which is filled with water. This, for example, water molecule 1. This is the second water molecule, for example. This is the third water molecule, for example. This is one more water molecule, which I'm showing you over here. Now, first of all, in case of water, if I talk about this particular bond is between oxygen and hydrogen. So which one is more electronegative? Oxygen. So this bond pair will be shifted towards oxygen. This bond pair will be shifted towards oxygen, due to which oxygen will be carrying delta negative charge. Oxygen will be carrying everywhere delta negative charge. Oxygen will be everywhere carrying delta negative charge. Now, for example, imagine that you are introducing Na positive gas into this container. You are introducing Na positive gas into this container. Now, what's going to happen? Can I say this negative end of water, this oxygen carrying negative, it's going to attract this Na positive towards itself? Absolutely. This oxygen carrying negative will attract this Na positive towards itself. Here will be the attractions. Here will be the attractions. And due to the attractions, energy is released. Due to the attractions, energy is released. Now, remember the amount of energy that is released when 1 mole of gaseous ion undergoes hydration. First of all, this phenomenon is called as hydration. And the amount of energy which is released when 1 mole of gaseous ion undergoes hydration is what you call as the hydration energy. Since energy is released means it is exothermic. And for all the exothermic processes, delta H value is taken as negative. Okay. Again, simple. So the amount of energy which is released when 1 mole of gaseous ion undergoes hydration. Perfect. Since energy is released during this process, so the process is going to be exothermic. And when it comes to the exothermic processes, delta H value will be coming out to be negative. Okay. Now this hydration energy, if I talk about this hydration energy, hydration energy is also directly proportional to the charge on ion and inversely proportional to the size of ion. It is also directly proportional to the charge on ion and inversely proportional to the size of ion. It's pretty much simple. More the charge on the ion, more will be the attractions. More the attractions, more energy released. More energy released, more the hydration energy. Simple. Right? Similarly, lesser the size of ion, more the charge density on the ion. For example, this is one ion which has got this much of size, carrying positive charge. One more ion having same charge. One more ion having same magnitude of charge, but size is more. I've taken 2 ions, for example. Both the ions are having same magnitude of charge on them, but size of this ion is less, size of this ion is more. So I would say, if I ask you, which ion will have more positive charge density? I would say more charge density will be on this particular ion. And more the charge density on the ion, more water molecules will be associated with it. And more water molecules associated with it means more will be the attraction. More attraction means more energy released. More energy released means more is the hydration energy. Right? Am I clear? So just one thing you have to remember, what is that? Your hydration energy is directly proportional to charge on the ions and inversely proportional to, again, the size of the ions. Now, my dear students, give the answer of all these questions, and I believe you should be in a position to do it quickly. Right? Yes? When you introduce basically an ionic compound in water, first of all, lattice energy plays a role, which breaks the force of attraction between them. Then comes your hydration energy. Am I clear? Am I clear, people? All clear till here? Say it once in the chats, guys, so that I can move on. Okay, I believe this is clear to everyone. Now have a look. Na positive, Li positive, K positive, or Rv positive. Give the hydration energy order. It's pretty much simple. Hydration energy directly proportional to charge, inversely proportional to size. Magnitude of charge everywhere is same. Now talk in terms of size. Lesser the size, more the hydration energy. Lesser the size, more the hydration energy. Okay. Now, this is La positive, Na positive, K positive, Rb positive. You have to talk about their size. I'm not talking about the hydrated size. I'm talking about the size when they are in gaseous state. When they are in gaseous state. What is the order of their size? Rb positive has got maximum size, followed by K positive, followed by Na positive, followed by Li positive. Okay. This is the order of their size. Now, if the size of Li positive is least, can I say Li positive will have maximum charge density among all these? Will have maximum charge density among all these? If Li positive has got maximum charge density among all these, can I say maximum water molecules will get attached with what? Maximum water molecules will get attached to Li positive. If in case of Li positive, maximum water molecules are getting attached. This entire size, Li positive including this water, is what I call as Li positive aqueous basically. Li positive aqueous. If I talk about the hydrated size order, this is called as now hydrated size. This is now called as hydrated size of Li positive. What is the order of hydrated size? It's pretty much simple. Since Li positive undergoes maximum hydration, so maximum water molecules are associated with Li positive, due to which the hydrated size of Li positive becomes maximum, right? So now the hydrated size order is going to be this. Okay, be careful with these. This was Li positive gas. This is Li positive aqueous. Okay, now tell me one thing. Since the size of hydrated Li positive is maximum, that means it has become bulky. If it has become bulky, will it show more moment or less moment? It will show less moment. That means its mobility now will be least, right? So Li positive aqueous, its mobility will be least. And lesser the mobility of the ion, lesser is going to be the conductivity. Lesser the mobility of the ion, lesser is going to be the conductivity. Is all of this clear to everyone? Yes? Again, simple guys, right? Now, my dear students, let's talk about something about covalent bonds. So first of all, I'll show you how to draw the structures of different covalent compounds. How to draw the structures of very simple covalent compounds, basically, as per Lewis theory is concerned. So as per Lewis theory is concerned, how do we draw the structures of different molecules? That is the point. Try to understand how do we draw the structures of some simple molecules as per the Lewis theory. Okay, try to understand very properly what I'll be saying. For example, you have got carbon monoxide molecule, CO. Okay, you have got CO. You have to draw its structure. You have to draw its Lewis structure. How do you draw it? First of all, tell me about one thing. How many valence electrons are there with carbon? 4 valence electrons. How many valence electrons are there with oxygen? 6 valence electrons. So in total, how many valence electrons do you see? 10 valence electrons. 10 valence electrons means how many valence electron pairs? 10 valence electrons means 5 valence electron pairs. 10 valence electrons means 5 valence electron pairs, right? Now, basically, you have to adjust these 5 valence electron pairs among carbon and oxygen. So what do you do? For example, this is carbon, this is oxygen, right? One side carbon, one side oxygen. Now do one thing. Just place a single bond first. Place a single bond first. This is your first step. Place a single bond. Single bond means you have used one electron pair. Because one bond means one electron pair. One bond means one electron pair. So out of 5 valence electron pairs, you have used one electron pair. So how many electron pairs are left? Out of 5, you have used 1. So 4 valence electron pairs are left. Now, which one is more electronegative element? Oxygen. Oxygen is more electronegative. So try filling the octet of oxygen. So I would say 1, 2, 3, 4, 5, 6, and 7, 8, since it's a covalent bond. So octet of oxygen is completed. Octet of oxygen is completed. Now tell me, out of 5 valence electron pairs, how many valence electron pairs we have used? 1, 2, 3, and 4. Out of 5, we have used 4. So 1 is still left. Give that 1 to carbon. Give that 1 electron pair to carbon. So can I say I've utilized all the 5 valence electron pairs? Absolutely. Octet of this oxygen is complete. But is the octet of this carbon complete? 2, 4. Only 4 electrons. Octet of carbon is not complete. So it is a time to fill the octet of carbon. For that, what do we do? This is the oxygen. Remove one of the electron pair. And instead of that, place a bond. remove one more electron pair. Instead of that, place a bond. Now check the octet of both the atoms. The octet of carbon, 1, 2, 3, 4, 5, 6, 7, 8 is complete. Octet of oxygen, 1, 2, 3, 4, 5, 6, 7, 8 is complete. So octet of both atoms is complete, right? Octet of both atoms is complete. Now there is one more thing that's asked. What is that? That is, calculate the formal charge. Calculate the formal charge on the atoms. So if I talk about formal charge on carbon first, then I'll be talking about the formal charge. Then I'll be talking about the formal charge on oxygen. How do we exactly calculate formal charge of carbon and formal charge of oxygen? Understand, there is a rule, simple rule for it as well. See guys, formal charge of carbon. Tell me one thing. Whenever carbon will be in non-bonded state, isolated, non-bonded state, how many valence electrons carbon has? In non-bonded state, carbon has 4 valence electrons, minus. Right now, carbon is in bonded state. So how many valence electrons it has? 1, 2. 1, 2. Now from this bond, I'll be just considering 1 electron. From this bond, I'll be considering 1 electron. From this bond, I'll be considering 1 electron. Perfect. So 1, 2, 3, 4, 5. So 4 minus 5 is equal to minus 1. This is the simple way by means of which you can calculate formal charge on carbon. Similarly, talk about the formal charge on oxygen. When oxygen will be in non-bonded state, how many valence electrons will it have? 6 minus. Right now, how many it has? 1, 2. Consider 1, 3, 4, 5. So 1, 2, 3, 4, 5. 6 minus 5 is plus 1. So the formal charge on carbon is minus 1 and the formal charge on oxygen is plus 1. Again, simple. Let me take a few more examples. With that, things will be more clear to you. For example, you have got, for example, NO2 negative. You have got NO2 negative. Now try to understand what I'll be saying. First of all, how many valence electrons are there in total? Nitrogen has got 5 valence electrons. Oxygen has got 6 valence electrons. And there are 2 oxygen atoms. There is a negative charge. Add that negative charge. If it was positive, then you were supposed to subtract it. There is a negative, so add it. So how much it will come out to be? 5 plus 1, 6. 6 plus 12 is 18. So there are in total 18 valence electrons. 18 valence electrons means how many valence electron pairs? 18 valence electrons means 9 valence electron pairs. So basically you have to adjust all these 9 valence electron pairs now. You have to adjust all these 9 valence electron pairs now. Now how do you adjust all these 9 valence electron pairs? Let's try to understand. First of all, for example, this is your nitrogen, this is your oxygen, this is your oxygen, right? Place a bond here, place a bond here. So out of 9 valence electron pairs, how many electron pairs I've used? 1 and 2. 2 electron pairs I've used. 2 electron pairs I've used. Now tell me one thing, which one is more electronegative, nitrogen or oxygen? Oxygen is more electronegative. So try filling the octet of oxygen. So I would say 1, 2, 3, 4, 5, 6, 7, 8. Complete. 1, 2, 3, 4, 5, 6, 7, 8. Complete. So out of 9, how many I've used? 1, 2, 3, 4, 5, 6, 7, 8. 8 electron pairs I've used. There is 1 electron pair left. Give that electron pair directly to nitrogen. Okay. Now check the octet of all the atoms. Check the octet of all the atoms. Octet of this oxygen is complete. Octet of this oxygen is also complete. But is the octet of this nitrogen complete? Have a look. 2, 4, 6. Just 6 electrons. It is not complete. So what am I supposed to do? Just select any of the oxygens. Any of. Whether this or this. The choice is yours. For example, I'm selecting this. Remove the electron pair and place a bond instead of that. Now, this is going to be the structure of NO2 negative. Now, my dear students, the point is, how do I calculate formal charge on different atoms here? For example, I have to calculate formal charge on this particular oxygen. I'm calling this oxygen number 1. This is your oxygen number 2. This is your atom number 3, right? Formal charge of first atom. That means formal charge of this oxygen. When oxygen is in non-bonded state, it has got 6 valence electrons. Minus. Right now, how many it has? 1, 2, 3, 4, 5, 6. And out of these 2, only 1. So it's 7. So 6 minus 7 is minus 1. What is the formal charge of the second atom? Second atom is again oxygen. So in non-bonded state, 6 valence electrons. Right now, 1, 2, 3, 4, 5, 6. So 6 minus 6 is 0. Right? Similarly, formal charge on this particular nitrogen. Formal charge on nitrogen will be how much? When nitrogen is in non-bonded state, 5 valence electrons. Right now, how many it has? 1, 2, 3, 4, and 5. Right? So 5 minus 5 is 0. So you have calculated the formal charge on these atoms as well. I believe it's clear to everyone. Yeah? I believe, people, it's super clear to everyone. If yes, let me know quickly in the chats. All clear till here? Should I move on? Or do you want one more example on it? Tanuja, I've given the simplest formula to calculate formal charge. You can remember this. Okay? Okay, let me take one more molecule. With that, things will be more clear. Okay? Now, people, you have got CO3 dinegative. So let's try to make it structure as well. So first of all, if I talk about carbon, how many valence electrons carbon has? 4. Oxygen has got 6 valence electrons. There are 3 oxygen atoms. There is dinegative charge as well. So add these two. Add these 2 electrons because of the dinegative. So it's going to be 4 plus 6, 3, 18. That is 22. 22 plus 2 is 24. So there are in total 24 valence electrons. So I would say there will be some 12 valence electron pairs. There will be in total some 12 valence electron pairs. Now we have to adjust all these valence electron pairs here. How do I adjust? For example, this is carbon. This is one more oxygen, one more oxygen, one more oxygen. So this is CO3 basically. Now give a single bond everywhere. Given a single bond everywhere. Okay. Every bond is single here. Now, my dear students, tell me one more thing. Tell me one more thing. Out of 12 valence electron pairs, how many we have used till now? First valence electron pair, second, third. We have used 3 valence electron pairs till now. So how many valence electron pairs will be left? Out of 12, 3 are used. So 9 will be still left. 9 will be still left, right? Now, my dear students, fill the octet of more electronegative elements. More electronegative element here is oxygen. So I'll try filling the octet of oxygen. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So how many valence electron pairs I had? 12. Out of 12, how many I've used? 3 plus 3 is 6, plus 3 is 9, 10, 11, 12. I've used all the 12 valence electron pairs here, right? Now check the octet of all the atoms. Octet of this oxygen is complete. Octet of this oxygen is even complete. Even the octet of this oxygen is complete. But, if I ask you whether the octet of carbon is complete or not, the octet of carbon is not complete. It has got 2, 4, 6, only 6 electrons. Now what do? It's your choice. Select any of the oxygen atoms. Let me select this oxygen atom, remove the electron pair, and instead of that, put a double bond, right? And this is the structure of your CO3 dinegative. Now let's try to calculate the formal charge. Let me call this as atom number 1. Let me call this as atom number 2. And let me call this as atom number 3. Now, my dear students, if I talk about the formal charge on atom number 1, formal charge on this oxygen. When oxygen is in non-bonded state, it has got 6 valence electrons. Oxygen in non-bonded state, 6 valence electrons, minus. How many right now? 1, 2, 3, 4, 5, 6, and just 1, 7. So 6 minus 7 comes out to be minus 1. Right? Formal charge on this particular oxygen, I would say that means formal charge of atom 2 I'm talking about. When oxygen is in non-bonded state, 6 valence electrons minus. Right now, how many it does? 1, 2, 3, 4, 5, 6, and 7. So 6 minus 7 is again going to be minus 1 only. What is the formal charge on this particular oxygen? I would say formal charge on oxygen number 3 will be in non-bonded state 6 valence electrons minus right now 1, 2, 3, 4, 5, and 6. So 6 minus 6 is 0. So these are the formal charge on different atoms which we have calculated again. If I'm clear, let me know once in the chats, people. In the chats, everyone. Everyone means everyone. Yeah? Perfectly done. Now, I believe you can easily draw the structures of some simple molecules. Again, I'm telling you, Lewis could not draw the structures of all the molecules. It could only draw the structures of few molecules, some simple molecules, right? For example, there are odd electron species. How do you draw their structures? No idea, right? Perfect. So basically, the point is Lewis could. What are you saying? Carbon. Oh, okay. You want to calculate the formal charge on carbon as well? Okay, do that. Do that. You can calculate it, right? When carbon is in non-bond state. 4 valence electrons right now. 1, 2, 3, 4. So 4 minus 4 is 0. Guys, it's already understood. You need not to calculate it now. See, it is CO3 dinegative. CO3 dinegative. So there is total 2 negative charge on the molecule, out of which 1 negative is already there. So minus 1 is minus 2. So definitely other atoms will be 0, 0. Yeah? All right. Now let's move on and talk about few more things. Let's move on and talk about few more things. There is one very, very, very important topic on which question is almost asked every year. What is that? Fajan's rules. Yeah? Fajan's rules. What these Fajan's rules say exactly? Where they are used? What kind of questions can be framed? What kind of questions can be asked from it? Let's get to know about that now. Okay? Let's get to know about the Fajan's rules now. My dear students, let me first of all tell you, no bond is 100% ionic or 100% covalent. No bond is 100% ionic or 100% covalent. This is the first point which you should know. No bond is 100% ionic or 100% covalent. In every covalent bond, there will be some ionic character. And in every ionic bond, there will be some covalent character. Since there is no bond which is 100% covalent, there is no bond which is 100% covalent or 100% ionic, every ionic bond has got some covalent character. Even every covalent bond has got some ionic character. Okay, this is the first point which you need to remember, my dear students. Now, as I told you, every covalent bond contains ionic character and every ionic bond contains the covalent character. Covalent character in an ionic bond. Covalent character in an ionic bond. It cannot be measured, but can be compared. Covalent character in an ionic bond. It cannot be measured, but it can be compared. Compared through what? Compared through certain rules, which are called as Fajan's rules. So where these Fajan's rules are used, I would say Fajan's rules are used to compare the covalent character in different ionic bonds. Okay? There are some rules which are used to compare the covalent character in different ionic bonds. Okay? Now, what these Fajan's rules says? Let's talk about that. My dear students, before talking about the Fajan's rules exactly, let me tell you one important point here. For example, you have got an atom A. Right? Let's say, for example, this atom here, A, has got some 7 electrons and 7 protons. This atom A, it has got some 7 electrons and 7 protons, for example. Right? That means this atom is neutral. Perfect. So can I say 7 protons are basically holding 7 electrons? Absolutely. 7 protons are holding 7 electrons. 7 protons are holding 7 electrons. Now, if you take 1 electron out, of it, right? What do we get? We get A positive. If you take 1 electron out of it, you get A positive. Now, in A positive, there will be 7 protons, but there will be only 6 electrons. Earlier, 7 protons were holding 7 electrons. Now, same 7 protons are holding only 6 electrons. Earlier, 7 protons were holding 7 electrons. Now, the same 7 protons, they are holding only 6 electrons. And I say force of attraction experienced by the electron here will be comparatively more. The force of attraction experienced by the electron here will be comparatively more. What does that mean? You can say, in terms of effective nuclear charge, you can say when an atom gets converted into the cation, when an atom gets converted into the cation, what happens to effective nuclear charge? I would say effective nuclear charge, that increases. Right? Effective nuclear charge increases. You can relate it with attractive power as well. What happens to attractive power? I'll say attractive power will increase. Attractive power will increase. When an atom gets converted into its cation, right? Attractive power increases because effective nuclear charge increases. Similarly, for example, you have got an atom A. This is the atom A, contains 7 electrons, 7 protons. Perfect. Now give 1 electron to this. When you give 1 electron to this, what do you get? You get A negative here. You get A negative. Now it will have 8 electrons but only 7 protons. So now you tell me, when an atom gets converted to the anion, tell me what happens to effective nuclear charge. I would say effective nuclear charge will decrease now, due to which attractive power, what happens to that? That again decreases, right? So 2 points which I would want every one of you to remember. And what are those 2 points? When the parent atom gets converted into the cation, effective nuclear charge increases, or you can say attractive power increases. When the parent atom gets converted to the anionic form, right? Effective nuclear charge decreases, or you can say attractive power decreases. Now, why am I telling you all this? Because I would need this particular point over here in Fajan's rules. Why do we need this? For that, you need to understand few points, my dear students. You need to understand few points. Just a second. Yeah, this particular slide. Look at this particular slide, guys. Just read it once, then I'll make you understand. When a cation approaches an anion, the distortion of electron cloud of anion takes place. And the phenomenon is called as polarization. When a cation approaches the anion, the electron cloud of anion gets distorted. This phenomenon is called as polarization. This phenomenon is called as polarization. And due to polarization, covalent character gets developed in an ionic bond. And covalent character in an ionic bond is directly proportional to polarization. Now, let's try to understand all these points over here one by one. See, guys. For example, this is your cation. This is some cation, okay, which contains positive charge. Right? And for example, this is your anion. Anions are generally bigger in size, right? And this anion carries the negative charge, right? So I would say this is basically the electron cloud of this anion. It is the electron cloud of the anion. Perfect. Definitely is the electron cloud of the anion. Now, my dear students, tell me one thing. First of all, this is cation, this is anion, right? Whenever you see cation and anion, there will be electrostatic force of attraction, which is called as ionic bond. So what is going to happen? When this cation will start moving towards anion, when this cation will start approaching towards anion, what's going to happen? Since the cation contains a positive charge, it carries the positive charge. So I would say this cation, it's going to attract the electron cloud of anion towards itself. When the cation approaches the anion, I would say this cation is going to pull the electron cloud of anion towards itself, due to which some portion of electron cloud will be shifted in this direction. Due to which some portion of electron cloud of anion will be shifted in this particular direction. Right? This is what you call as the distortion of electron cloud. I would say the electron cloud moves slightly in this particular direction. Right? And this particular thing is what you call as distortion of electron cloud. This is what you call as the distortion of electron cloud. And my dear students, the phenomenon, when the cation approaches the anion, the electron cloud of anion gets distorted. It comes towards the anion. This distortion is called as polarization. And due to polarization, what happens? Covalent character is generated. Covalent character is induced in an ionic bond. How this covalent character is induced? My dear students, think logically. If the electron cloud is coming in this particular direction, if the electron cloud is slightly shifted in this particular direction, and I say this electron cloud is basically coming in between them, this electron cloud is coming in between cation and anion, as if there is some mutual sharing of there is some mutual sharing of this particular part of electron cloud happening between these two. It is as if there is some mutual sharing of this part of electron cloud happening between these two. Mutual sharing means covalent. Mutual sharing means covalent. Right? Yeah? Perfect. So in short, let me quickly summarize it. When the cation approaches the anion, what happens? Electron cloud of the anion gets distorted. And this distortion of electron cloud is something which we call as polarization. Right? This distortion of electron cloud is something we call as polarization. And due to polarization, covalent character gets generated. It gets induced in an ionic bond. It gets induced in an ionic bond. And remember, more the distortion of electron cloud, that means more the polarization. More the polarization means more will be the covalent character in an ionic bond. Okay. Now, my dear students, this polarization, it depends on two factors. Polarization depends on two factors. Number one is called as the polarizing power of cation. Number one is called as polarizing power of cation. And number two, polarization, it's directly proportional as polarizability of what? Of anion. So basically, polarization, it actually depends on two things. One is your polarizing power of cation. Another one is your polarizability of anion. Now, what is polarizing power of cation? Polarizing power, my dear students, which is also called as ionic potential. So let me tell you this polarizing power of cation. It is first of all defined for cations. And how do we define the polarizing power? It is simply the tendency of the cation. The tendency of the cation to distort the electron cloud of anion. The tendency of the cation to pull the electron cloud of the anion towards itself. The tendency of the cation to distort the electron cloud of anion. The tendency of the cation to pull the electron cloud of anion towards itself. Okay? And you know, more the tendency of the cation to pull the electron cloud of anion towards itself, I would say more will be the polarization. And more polarization means more covalent character. Right? So remember, your covalent character, it's in short directly proportional to the polarizing power of cation. Now you must be thinking on what parameters the polarizing power of cation depends upon. Again, two factors. Polarizing power depends on directly proportional to the charge on cation, inversely proportional to the size of cation. Polarizing power of a cation. It is directly proportional to the charge on cation and inversely proportional to the size of cation. Okay? You just remember this directly. This is sufficient for you. So basically, I would say, if I quickly summarize it, when the cation approaches the anion, the cation pulls the electron cloud of anion towards itself. This phenomenon is called as polarization. And due to polarization, covalent character gets induced in an ionic bond. Right? And my dear students, this polarization depends on two factors. One is called as polarizing power of cation. Second one is called as polarizability of anion. Polarizing power is also called as the ionic potential. And polarizing power, it gives us the tendency of the cation to distort the electron cloud of anion. It gives the tendency of the cation to pull the electron cloud of anion towards itself. And my dear students, more the tendency of the cation to pull the electron cloud of anion towards itself, more the polarization. More the polarization, more is the covalent character. Right? Yeah? Perfect, people. I believe this is clear to everyone. And as I told you, polarizing power, it depends on two factors again. It depends on the charge on cation and inversely proportional to the size of cation. Right? Which is easily justified as well. Similarly, there is something called as polarizability. What is polarizability? As I told you, polarizability term. Polarizability, it is defined for anions. And polarizability is basically the tendency of anion to distort its electron cloud. the tendency of an anion to distort its electron cloud. Right? The tendency of an anion to distort its electron cloud. More the tendency of an electron cloud to distort its, more the tendency of the anion to distort its electron cloud, more will be its polarizability. What does that mean? Try to understand. For example, this is your one anion. For example, this is your one more anion. Let's say. So what happens basically? This is the electron cloud of this anion. Even this is the electron cloud of this anion. Right? Where is the electron cloud bigger in size? Electron cloud is bigger in size here. Can I say this nucleus will be attracting its electron cloud towards itself? Yes. The nucleus will be attracting its electron cloud towards itself. Over here also nucleus will be attracting its electron cloud towards itself. Now you tell me, among these two cases, where can we distort the electron cloud easily? Since this electron cloud is bigger in size, nucleus will be holding this electron cloud towards itself. But the tendency with which this nucleus, the force of attraction which this electron cloud will be experiencing from the nucleus will be more. The force of attraction which this electron cloud will be experiencing from its nucleus will be more because size of the electron cloud is less. Here the size of electron cloud is more. So this electron cloud will be experiencing comparatively less force of attraction from its nucleus. Right? So you can easily distort this particular electron cloud as compared to this one. Right? You can easily distort this particular electron cloud as compared to this one. And the tendency of an anion to distort its electron cloud gives you the polarizability of the anion. Right? Gives you the polarizability of the anion. Perfect? Gives you the polarizability of an anion. And let me tell you, this polarizability, it talks about the covalent character in an ionic bond. If I say an anion has got more polarizability, that means an anion has got more tendency to distort its electron cloud. That means its electron cloud can be distorted easily when the cation will approach towards it. And if its electron cloud can be distorted easily, that means more will be the polarization. More polarization means more covalent character. So I would say in short, your polarizability is directly proportional to covalent character is directly proportional to polarizability. And again, one more thing. This polarizability, which is defined for anions, let me tell you, which directly you are going to remember, it's directly proportional to the charge on anion. Polarizability is directly proportional to charge on anion. Also, this polarizability is directly proportional to the size of anion as well. Remember these 2 points. Okay. So in short, if I summarize it, covalent character in an ionic bond, right? Which will be definitely inversely proportional to ionic character. Because covalent ionic will be inversely, right? So covalent character depends on what? It depends on polarizing power. Polarizing power of what? Of cation. And also this covalent character depends on the polarizability. The polarizability of what? Of the anion. Now, at the same time, my dear students, remember one more thing. As I told you already, this polarizing power of cation depends on charge on cation inversely proportional to size of cation. Right? Similarly, polarizability. It is defined for what? It's defined for anions. It's directly proportional to charge on anion and also directly proportional to size of anion. These are few points which you need to remember, and I believe you can easily solve the questions, right? Yeah? Am I clear? People? Tell me the answer of these basic questions here. Arrange in the order of the polarizing power. Li positive, B di positive. Talk about charge first. More the charge on cation, more is its polarizing power. More charge, more polarizing power. More charge, more polarizing power. More charge, more polarizing power. Simple. Yeah? Okay. Give me the polarizing power of these cations. If you look carefully, the charge on every cation is same. So I'm not going to decide on the basis of charge. I'll be deciding on the basis of size. Lesser the size, more the polarizing power of the cation. Lesser the size, more the polarizing power. Again, the charge on every cation is same. So talk in terms of size. Lesser the size, more the covalent character. So B di positive has got minimum size among all. So it will be having maximum polarizing power. Yeah. It will be having maximum polarizing power. Now, my dear students, one more thing. Polarizing power, which I told you already, it's also called as ionic potential. And this polarizing power, which is defined for cations, it depends on what? It depends on effective nuclear charge. Polarizing power, it depends on effective nuclear charge. In case of which elements? In case of d block elements. In case of d block elements, your polarizing power, first of all, polarizing power, it depends on the effective nuclear charge, right? In case of what? In case of d block elements. And generally, if you know, in case of d block elements, on moving from left to right, in case of d block elements, on moving from left to right, generally, Z effective increases. Z effective increase means attractive power increase. Attractive power increase means polarizing power increases. So in case of d block elements, generally, on moving from left to right, polarizing power increases. Okay. And if you move from top to bottom, from 3D to 4D, 4D to 5D, right? Again, polarizing power increase. Again, polarizing power increases. Right? Because on moving from top to bottom, again, Z effective increases in case of d block elements, generally, right? And if Z effective increases, Asif, beta ishi English channel, ठीक है? ये चीज़ कशिर पर काथमा करने के, ये तो अनपढ़ का चुक सो. अगर ने English channel ऐसे भी कराना, English पर काथ के थे, by the way, ठीक? थोड़ा सा मगजन कम है वहाँ. So I believe this is clear, guys. Yeah. I believe this is clear to everyone. Perfect. So in case of D block elements, remember when you move from left to right, your Z effective increases. When you move from top to bottom, again Z effective increases. And if Z effective increases, what's going to happen? The polarizing power automatically increases. Yeah? Okay. Now look at this particular one. Can you give me the order of polarizing power here? Quickly. See, Fe di positive, cobalt di positive, nickel di positive, copper di positive. On moving from left to right. On moving from left to right. On moving from left to right. What happens to effective nuclear charge in case of d block elements? Increases. So Z effective increases. Z effective increases. That means polarizing power automatically increases. Right? Zinc di positive, cadmium di positive, Hg di positive. Let me tell you this is a 3D element. This is 4D. This belongs to 5D. Right? On moving from top to bottom, from 3D to 4D, 4D to 5D, Z effective again increases. And if Z effective increases, I would say polarizing power automatically increases. Now, my dear students, tell me the answer of this particular question as well. Arrange the following in the order of polarizability. Polarizability is defined for what? Polarizability is defined for what? It is defined for quick anions. And polarizability depends on two factors. Charge on anion, size of anion. And polarizability is directly proportional to charge on anion, also directly proportional to size of anion. Now, N tri-negative, O di-negative, F negative. Where is the charge on anion more? Here, more the charge on anion, more the polarizability. Right? More the charge on anion, more the polarizability of anion. Perfect. F negative, Cl negative, Br negative, I negative. Charge on every anion is same. Now talk in terms of size. More the size of anion, more the polarizability. More the size of anion, more the polarizability. Simple. Similarly, O di-negative, S di-negative. Charge on anion is same. Talk in terms of size. Oxygen and sulfur, they are in the same group. Down the group size increases. More the size, more the polarizability. More the size, more the polarizability. Simple. As simple as that, I must say. Correctly done, people? Correctly done? Now tell me the answer of all these questions. Arrange the following on the basis of the covalent character. Arrange the following on the basis of their covalent character. This is basically zinc di positive. This is Cl negative. Cadmium di positive, Cl negative. Hg dye-positive, Cl negative, right? See, anion everywhere is same. So I'm not going to decide as per anion. I'll be talking in terms of cation. I'll be talking in terms of cation. The charge on every cation is same. The charge on every cation is same. If you look carefully, this is zinc dye-positive, 3D, 4D, 5D. 3D to 4D, 4D to 5D. Z effective increases. Z effective increase means polarizing power increases. And more the polarizing power of the cation, more is going to be the covalent character. This is the order of covalent character. Because covalent character is directly proportional to polarizing power of cation. Things we have already discussed. This is zinc dye-positive, S dye negative. Cadmium dye-positive, S dye negative. Hg dye-positive, S dye negative. Anion again, everywhere same. Talk in terms of cation. Zinc dye-positive, cadmium dye-positive, Hg dye-positive. Again, this is 3D, this is 4D, this is 5D. More the polarizing power of cation, more the covalent character. Simple. Right? Now, my dear students, Li positive, F negative, Na positive, F negative, K positive, F negative, Rb positive, F negative, cesium positive and F negative. Okay, cesium positive and F negative. Okay, now, F negative everywhere same. Now talk in terms of cation. The charge on every cation is same. So decide on the basis of size. Lesser the size of the cation, lesser the size of the cation, more is the polarizing power of cation. And more the polarizing power of cation, more is the covalent character. This is the order of covalent character. Now this is Be dye-positive, this is F negative. This here Be, okay? Be dye-positive, Cl negative. Be dye-positive, Br negative. Be dye-positive, I negative. So first of all, the cations here everywhere are same. So don't talk in terms of cation, talk in terms of anion. Since the charge on every anion is same, so talk in terms of size, right? More the size of anion, more the polarizability of anion, and more the polarizability of anion, more is the covalent character. Simple thing which we have discussed already. Okay. Give me the order of this one. Arrange in the order of the covalent character. Arrange in the order of covalent character, people. Quick. Quickly, everyone. See, you've got aluminum tri-positive F negative, Al tri-positive Cl negative, Al tri-positive Br negative, Al tri-positive I negative, right? So cation everywhere here is same, so I'm going to talk in terms of anion. The charge on every anion is same, so decide on the basis of size of anion. More the size of anion, more the polarizability of anion, more the covalent character, right? Similarly, Mg dye-positive F negative, Mg dye-positive Cl negative, Mg dye-positive Br negative, Mg dye-positive I negative. Again, this is going to be the order of the covalent character. Again, F negative, Cl negative, Br negative, I negative. This is the order of covalent character. F negative, Cl negative, this is the order of covalent character. And reverse of the order of covalent character, reverse of the order of covalent character is going to be the order of ionic character. Yeah? Right, people? I believe all this stuff is like super clear to everyone. I believe all this stuff is super clear to everyone. Now, guys, understand this particular concept. Understand this particular concept. This is Cu positive here. This is Cl negative. This is Na positive. This is Cl negative. Right? Okay. So the cation here is Cu positive. The cation here is Na positive. If I talk about what is the configuration of Cu positive, configuration of this Cu positive is xenon. With xenon, you'll write 3d10. Right? Configuration of Na positive will be what? What will be the configuration of Na positive? Na positive. Quick. It will be simply configuration of neon. Right? Configuration of neon. Now, my dear students, whenever you see such kind of configuration, what configuration? Inert gas configuration followed by D10. Inert gas followed by D10 configuration. Inert gas followed by D10. This is what you call as pseudo inert gas configuration. And this is normally called as inert gas configuration. One is pseudo inert gas configuration, one is inert gas configuration. My dear students, remember one simple thing. Polarizing power of that cation that has got pseudo inert gas configuration is more. Polarizing power of that cation which has got pseudo inert gas configuration is more than that of the cation which has got the inert gas configuration. Okay. Now, my dear students, which has got more polarizing power? You tell me now. It's going to be Cu positive, which has got more polarizing power than that of Na positive. And more the polarizing power of the cation, more is going to be the covalent character. CuCl is going to be more covalent than that of Na positive. Right? Okay? Remember this particular point as well. This is again very, very, very important. Is it clear? I believe all the things are clear till here. Yeah? I believe all the things are clear till here. Now, my dear students, there are some applications of this Fajan's rules which I would want every one of you to remember. Okay? And what are these applications? Remember, first of all, solubility. Solubility. If I talk about solubility, okay? Solubility of ionic compound will be generally greater than that of covalent compound in polar solvent. Solubility of ionic compound will be generally more than that of the solubility of covalent compound. Which solvent? In polar solvent. I would say that molecule which will be having more ionic character, will be more soluble in polar solvent than that of the molecule which will be having more covalent character. This is the first thing which you have to remember. That's it. Only thing which you have to remember. Solubility of ionic compounds is generally more than that of covalent compounds. So that molecule which has got more ionic character will be more soluble in polar solvent. For example, you have got Ag2S and Ag2O. You have got Ag2S and Ag2O. Now understand. How to compare their solubilities. First of all, this is Ag positive, this S di negative. This is Ag positive, this O di negative. Cation is same. Talk in terms of anions. Charge on anion is same. Talk in terms of size. More is the size of sulfur than that of oxygen. More size of anion. That means more the polarizability. More the covalent character. More the covalent character, lesser the ionic character. This is the order of ionic character. And whatever is the order of ionic character, more the ionic character, more the solubility. Right? So this is the solubility order as well. Perfect. I would say Ag2S is less soluble than that of Ag2O. Or if you want to remember it in terms of formula, so remember solubility is directly proportional to ionic character and inversely proportional to covalent character. Perfect. Similarly, for example, you have got FeOH whole thrice and FeOH whole twice. FeOH whole thrice and other molecule you have got FeOH whole twice. This is basically iron tri-positive. This is OH negative. This is iron di-positive and this is OH negative. So anion is same. Talk in terms of cation. More the charge on cation. More the charge on cation. More the charge on cation, right? More the charge on cation. More the polarizing power of cation. More polarizing power means more covalent character. More covalent character means lesser ionic character, right? So this will have lesser ionic character. Lesser ionic character means lesser solubility. So I would say FeOH whole twice. FeOH whole thrice will be less soluble than that of FeOH whole twice. This is application number 1, which you have to remember. Application number 2. If you talk about melting point order, again, let me tell you, melting point of ionic compounds is generally greater than that of covalent compounds. Melting point of ionic compounds will be generally greater than that of covalent compounds. Or if you want to write it in terms of order, you will say melting point is directly proportional to ionic character and inversely proportional to covalent character. For example, take a look on all this. BeCl2, right? MgCl2, CaCl2, SrCl2, BaCl2. Beryllium, magnesium, calcium, strontium, barium. These are the chlorides of group 2nd, right? I have to arrange them on the base of their melting point. Now think logically. Cl negative, everywhere same. Talk in terms of cation. Be dipositive, Mg dipositive, Ca dipositive, Sr dipositive, barium dipositive. Charge on every cation is same. Talk in terms of size. Lesser the size of cation, more will be its covalent character. More covalent character. Basically, lesser the size of cation, more will be its polarizing power. And more the polarizing power of cation, more is the covalent character. More the covalent character, lesser will be the ionic character. Lesser ionic character means lesser melting point. So which one will be having maximum melting point? This one will be having maximum melting point, right? So melting point of BaCl2 will be maximum, followed by SrCl2, calcium CaCl2, magnesium Cl2, BeCl2, right? Remove this particular point as well. Now similarly, guys, when you talk about the thermal stability, again thermal stability follows the same order. Thermal stability of ionic compounds will be generally greater than that of covalent compounds. Or if you want to write the order, you can write thermal stability is directly proportional to ionic character, inversely proportional to covalent character. Now, you can easily give the order here. This is, for example, lithium carbonate, sodium carbonate, potassium carbonate, rubidium carbonate, cesium carbonate. When you move from top to bottom, what happens to covalent character? Tell me that. When you move from top to bottom, what happens to covalent character? The CO3 dinegative everywhere same. Li positive, least size, more covalent character. So down the group, covalent character decreases. If down the group covalent character decreases, that means down the group ionic character will increase. And more the ionic character means more is the thermal stability. So thermal stability order will also increase. Right? Thermal stability order will also increase. Perfect. When you move down the group. I believe this is clear to everyone. Okay. So my dear students, I think this much is enough for today. Okay. Tomorrow at 11 a.m. we'll have its part 2 and we'll complete the chapter exactly in the second session, which is tomorrow exactly at 11 a.m. Okay. So all the other things in this particular chapter, like dipole moment, like you have got VSCPR, like you have got hybridization, you have got MOT, you have got hydrogen bond, all that will be done in the tomorrow session. And tomorrow session is comparatively going to be lengthy. Okay. That will be 4 to 5 hours. Yeah, 5 hours minimum that it's going to take. So at 11 a.m. we are going to start tomorrow, right? And then you can count 5 hours and we'll be done with this particular chapter as well. But be there on time tomorrow exactly at 11 a.m. Okay? You can let me know in the comment section how you liked the session, right?